Yes, I welcome you all for another presentation on electronic devices and circuits subject in which we are continuously discussing about the transistor. So, if you recall our previous presentations, depending on these BJTs, we have been discussing about the BJT configurations. Okay, and in previous presentation we have seen that there are three types of basic configurations like common base, common emitter, and then common collector configuration, right? If you see in previous, this is what the continuation of the previous previous lecture itself, right? This is a common base configuration. This is a circuit of a common base configuration. Actually, it is the base terminal. Basically, if you see, this is the base terminal kept as a common with respect to the remaining two terminal, that is emitter terminal and then collector terminal. This is the base terminal basically, right? Okay, if you recall in previous presentations, there we have seen some important parameters like various that you can get from our previous presentation, right? In today's presentation, let us go little bit forward, right? So in this common base configuration, if you see, I can erase some unnecessary things from here. I think this is not required here, right? So just you focus on this particular circuit diagram. Even this is also not required now. Clear? So this particular expression is also not required. So if you just focus on this particular circuit, this is the very important configuration, common base configuration circuit, right? So in this basically, as we have kept the base as a common, now our input current, this is what emitter terminal, this is the emitter terminal in which the current flowing through is emitter current is the input current basically. This is the emitter current, which is the input current, nothing but emitter current. The emitter current is the input current. Why? The emitter terminal acts as input terminal in common base configuration. This is the circuit for common base configuration. As we kept base as common, means at zero potential, then your emitter terminal obviously will act as input terminal. Therefore, the current flowing through is called as input current, right? This already I have explained in previous presentation. And here this collector current, so this collector current IC will act as output current or otherwise collector current, right? So in this particular configuration, what will happen, the emitter current basically, or the input current will flows through this base terminal actually. So this will be passes through the base, and the collector current will collect this actually, right? Therefore you can write this, and again remember that here. So in already previous presentation I have explained you that the input terminal, the input junction otherwise means between emitter to base, this particular junction called as input junction, and this must be a forward biased. This must be forward biased. Whereas if you see the output junction that is there between collector to base, that must be reverse biased. Remember that, right? The input junction must be forward biased and the output junction must be reverse biased. If you connect the biasing voltage like this, then only the transistor will work as an amplifier. Okay, so that is the very important condition for a transistor, right? The input junction must be forward biased, whereas the output junction must be reverse biased. That is very mandatory requirement for a transistor which is to be operated as an amplifier, right? Now, so see that here, if you see at the output junction, as it is a reverse bias basically, what happens in PN diode? If you recall the diode concept, if you connect the PN junction diode in reverse bias condition, what will happen? In reverse biased condition, the the majority carriers, they will go away from the junction actually. They will go away from the junction, right? Okay, whereas in p-type as well as, let us, I will explain you here. This is very interesting concept actually. If you see, this is what your p-n diode, let us say this is p-type, this is n-type actually, and this is basically, it is a anode because it is a positive terminal plus, I mean holes are positive terminal, so these are positively charged, whereas electron, so in n-type majority are electron, therefore minus is taken. Now what is the reverse bias actually? Reverse bias is nothing but simply you change the battery actually. So battery is nothing but like this. So the plus terminal of the diode can be connected to the negative terminal of the battery, means this is negative, this is positive, whereas the negative terminal of the battery is connected to the positive terminal of the battery, right? That is what the reverse bias. So positive terminal is connected to the negative terminal of the battery. This is what the battery actually, or you can say some voltage or battery, whatever it is. So positive terminal of the battery is connected to the negative, I mean positive terminal of the diode. This is PN diode actually. Positive terminal is connected to the negative terminal of the battery, and the negative terminal of the diode connected to the positive terminal. Therefore this is called reverse bias condition. So in reverse bias condition, what will happen, you know? So here in p-type material, the majority carriers are holes, whereas in n-type material, the majority carriers are electrons, right? So these positives means the holes actually, or the positive, always the positive are attracted by the negative itself. Clear? The positive charge carriers, the positive carriers are attracted by the negative, as well as the negative are attracted by the positive. Means that what you know, that actually at this junction there is a small depletion layer will be there. In fact, there is a depletion layer, small amount of, small width of depletion layer will be there at the junction actually. Now the flow of these majority carriers are in this direction actually. They will flow like this. They will flow like this. These majority carriers will flow like this, and they will be attracted by this terminal. Their flow will be like this, like this. Similarly, the electrons will flow like this, like this. So they will flow like this. They are attracted by this one. So if you see that, what actually, what you can observe here, so here the whole direction is like this, the electron direction is like this, means that what, they are going away from the junction. They are going away from the junction, thereby the width of the depletion layer will also increases basically. Okay, so the width of the depletion layer will also increases, thereby there is no recombination of electrons and holes in reverse bias condition. Normally when you will get the electricity, when you will get the current, when you will get the conduction process, means conduction process is nothing but because of the process only we will get the current. Okay, whenever the hole as well as electron both will come together, both will recombine. They should combine actually to each other. Then only the conduction will takes place. That will happen in forward bias actually. But whereas in reverse bias condition, if you see, both are attracted away. They goes away from the junction. This is the junction. This comes, holes comes in this way, and your electrons goes in this way, and they goes away from the junction. There is no recombination here. Clear? Therefore there is no conduction in this reverse bias. That's why we can simply say that the current is zero in reverse bias condition. The current is zero because there is no recombination. Electrons and holes are, they are not combining to each other. That's why they are going away from the junction. Therefore there is no conduction process. As there is no conduction process, the current is zero because of majority carriers. But remember that one important point is that though the majority carriers go away from the junction, in p-type material there is a small amount of minority carriers will be there. Remember that. Okay, in p-type material, what are the majority carriers? Holes are the majority carriers. In fact, there is a small amount of minority carriers will also be there in p-type material. So what are the minority carriers in p-type material? Electrons obviously. So small amount of electrons will be there here in p-type material. As well as if you see the n-type material, there is a small amount of minority carriers will be there. So the majority are electrons here, and small amount of minority will also be there, and the minority are whole actually. So these minority carriers. So now see that in p-type material, so the electrons are minority, and in the n-type the holes are minority. So this is electron are negatively charged, they will be attracted by the positive. Therefore these the flow of this minority will be like this, forward direction. They will flow like this, in this direction. Similarly, here the in n-type material the minority are holes, they will be attracted by the negative terminal actually. That's why they should come in this direction. Means that the minority will come like this, and these will flows like this. Means that what? So they will travel to each other. They comes to each other. They come closer to each other and they will recombine, right? Therefore, therefore in the reverse bias condition, because of the minority carriers, and even the order of the minority carriers are very less. The order of the minority carriers are very less. Clear? But so because of this small amount of minority carriers, there is a small amount of conduction will takes place. That's why if you see that the order of the current in reverse bias condition is normal in microamperes. You can write the current in microamperes. It is 10 power minus 6 amperes, right? That is the reason why. So because of this minority carrier, the availability of minority carriers are less, right? So because of this minority carriers, okay, there is a small amount of reverse bias condition, reverse bias current. That current is called as reverse bias current, and the order is very less. It is in microamperes actually, right? The same concept, whatever we have seeing now, the same concept will applicable to in transistor also. So because if you see at the output junction, so this junction is biased in reverse bias condition, therefore small amount of reverse bias condition current will flows here. Now you can write the expression for the collector current in this transistor. If you see, the expression for collector current can be written as like this. So I will explain you the expression for collector current. If you see, so IC is equal to, you can write that alpha times IE plus a small amount of reverse bias current, that is called as ICBO. Remember that this is very important expression in common base configuration, right? What is IC? IC is your output current, nothing but collector current. Therefore, output current is equal to, so part of this, I mean alpha times IA means alpha times, this is the fraction actually, also called as amplification factor. Remember that current amplification factor, alpha is called as current amplification, right? Current amplification factor, that is called as current amplification factor. And always remember that is less than 1 only. The value of alpha is, it is less than or equal to 1, not greater than 1. It is less than or equal to 1 actually, right? So alpha times IE means alpha times input current plus reverse bias current means ICBO. It is a small current actually. You can call it as equation number 1. This you can call as equation number 1, right? Now I am arranging the circuit actually here, right? Just there is one important expression actually, that's why I want to explain that expression here, right? So what is the expression? I will write here again. So this is IC, output current is equal to alpha times IE plus ICBO. What is ICBO? You know, in common base configuration, this is the reverse bias current actually. Reverse bias current, also called as, sometimes this current is also called as leakage current, right? And this is, you can call it as equation number 1 as I have marked there. Now we know that what is IE actually, what is emitter current is equal to, it is IC plus IB. No, I mean collector current plus base current. This is called your equation number 2. Now substitute this equation number 2 in 1. So substitute, right? Substitute equation 2 in 1. What you will get, you know, IC is equal to, it is alpha. What is IE? IE is nothing but IC plus IB is equal plus ICBO, right? This implies it is alpha times IC plus alpha times IB plus ICBO. This is what I see. Now here bring this alpha times IC to the left side and take IC as common here, right? So you bring this IC to the left side, bring this alpha times IC to this left side, then take IC as common, then obviously your IC, if you take IC as common here, I suffix C, right, what you will get? It is 1 minus alpha, actually you will get 1 minus alpha is equal to, what you will get? Alpha times IB plus ICBO. This implies furtherly you can write IC is equal to, bring this 1 minus alpha to there, what you will get, you know, alpha by 1 minus alpha into IB plus ICBO by 1 minus alpha. This is the collector expression, output expression, common base configuration, very important, right? IC is equal to alpha by 1 minus alpha into IB plus ICBO by 1 minus alpha, where alpha is the amplification factor or also called as current gain. Actually it is output current by input current, remember that. So if ICBO is 0, assume that if ICBO is 0, then definitely IC is equal to alpha times IA, therefore alpha is equal to IC by IA. It is called as output current by input current, called as current gain. Okay, so what is the current gain value here? Obviously you can take it is 1, right? Ideal value is 1, ideal value is 1. Practically it could be less than 1 only, it is always less than 1, right? So this is what the expression, in very important expression. I think I will finish off here and I will continue the input and output characteristics of CB configurations in the next presentation. Means in input characteristics, what is the input characteristics? Nothing but we can study that input characteristics, nothing but it is the graph between input voltage to the input current. That is what the input characteristic. Similarly, what is the output characteristic? Output characteristic nothing but that is the graph drawn between output current and then output voltage. If you see in CB configuration, your input current is emitter current IE. What is the input voltage? That is the voltage between emitter to base, actually VEB. Therefore, VEB is the input voltage, IE is the input current. So we will plot a graph between IE versus VEB and we will see how the characteristics will change, means how the the graph will be looks like. Similarly, in output characteristics, the output current is collector current IC, whereas the output voltage is nothing but it is the voltage between collector terminal to the base, that is V suffix CB. Therefore, IC versus VCB, if you plot the graph and we will see the characteristics, right? So that is what actually, that is what the thing basically. Okay, so with this we will finish off here and we will see the subsequent presentations in the coming lecture. I hope you understood well and I wish you all to share and give your observations and comments, and definitely do not forget to share these things, these information to your friends wherever they are. And okay, so with this we'll finish off here and we'll meet in the next presentation. See you.